Okay, so sorry about the delays. So welcome everyone tonight to 60 Minutes in Space. I'm Chun Yu. I'm an astronomer here at the Denver Museum of Nature and Science. So welcome everyone, especially for those who are here for the first time. Let me just give you just a brief explanation, since there are a lot of people here who don't regularly come to this, of what we do. But 60 Minutes is a monthly program. It's the last Wednesday of each month. And what we do is cover space news that has come out in the past month. And I'm an astronomer, so I tend to look at things that are stars or galaxies or anything outside of our solar system. Although tonight I'm going to actually have a solar system story. And one of the unique things about this program is that I will look for stories and sort of give it my own spin. So you might have heard of some of these stories on if you browse the web or see a news report online. But what I try to do is sort of dig a little bit deeper into the story so that you get a deeper look at some of these astronomy stories. So with that, since we're running late, I'm going to jump right in. And what we're going to do tonight is first talk about this movie, which was announced just this past month. And this is an all-sky. And let's see if we can bring down the lights in the front so that we can see the screen better. But this is an animation showing gamma ray activity for the past year. Still waiting for the lights. But so if you can imagine the entire sky, looking out in every direction, but what you do is you flatten that sky, and what we're seeing is the Milky Way. And we can bring down the lights in the front. We don't need lights on me. Let's get better contrast on this. And so this sort of orange band is the Milky Way, and you'll see this yellow disk moving through the image, and that's actually our sun. So basically the sun over the course of a year. And so this is from the vantage point of the Hubble Space Telescope, and what we're seeing is gamma ray activity. So it turns out that the gamma ray sky is extremely active. And so this is just a wonderful animation showing all these sources, about 1,500 sources. And we'll learn in just a minute what those sources are. But the Fermi Gamma Ray Space Telescope was launched in 2008, so about 15 years ago. And it actually orbits the Earth about 320 miles above the Earth. And it's hard to figure out a scale here because there's no person next to it. But it's about the size of a decent-sized closet. So it's about 9 feet by 9 feet across at the base. So here is a spacecraft that launched it, and here is just an artist depiction of it in Earth orbit. And basically, the main instrument on it is something called the Large Area Telescope. And what it does is it detects these high energy photons, these gamma rays, from anywhere in the sky, and it uses basically a set of detection plates that help pinpoint where these photons are coming from. And then these high energy photons actually create pairs of electrons and anti-electrons. And those are measured down at the bottom, so you can actually figure out what energies these gamma rays are. And gamma rays are basically the most energetic part of the electromagnetic spectrum. So the light that our eyes can see, the visible part of the spectrum, is represented here. And there are infrared parts of the electromagnetic spectrum that's weaker in energy, like the infrared and microwaves and radio. And then there are photons, or part of the spectrum that's more energetic or more powerful. And so that includes ultraviolet, just past the violet part of the spectrum, and then X-rays, and then gamma rays are the most energetic. And it turns out that lots of things in the sky emit gamma rays. So Here's an image of our sun, and it turns out that the sun can have very energetic outbursts on its surface. You might have heard about coronal outbursts, and in fact, this past week, the Earth was awash in particles from such an outburst, and you might have heard about aurora being seen really far south. And these regions that generate these outbursts can also generate gamma rays. But for the most part, the sun doesn't produce a huge amount of gamma rays. For that, you have to go to sources like supernova remnants, which are and supernova explosions. Here's the Crab Nebula, which is a supernova that went off almost 1,000 years ago. And then also another huge source are black holes and the supermassive black holes at the centers of galaxies. And so at the center of our galaxy, as well as almost every galaxy that we've been able to observe very carefully, we find a central black hole engine with usually you have a toroid or a donut of gas and dust that orbits it. And as that material slowly spirals in, it gets jammed up, it gets heated, and it can be heated to tens of millions of degrees. And it's that heating that generates gamma rays, and it can also generate these jets that shoot out along the north and south poles of the black hole. And we actually see this. So these black holes tend to be very small. They're very difficult to see. But we can see them coming out of galaxies. So here's M87. We see jets that are tens of thousands of light years in length. And when we zoom out from a galaxy, we can see these jets plowing through the intergalactic medium. And it creates giant bubbles of gas and lots of radio emission. And what is happening, again, here's kind of a schematic. You have a central black hole. None of this is to scale. See that there. You have a black hole, and then you have this toroid, this big donut of gas and dust. And then here's that jet that I was talking about that comes out in either direction. And then it turns out that there's lots of gas clouds as well. And what astronomers have realized over the last several decades, going back 40 years now worth of observations, is that depending on how this system is oriented towards us, if we were looking straight down the barrel of this black hole system, then you're basically being exposed to all the radiation that's coming out of the black hole. So if a galaxy is oriented so that we're looking straight down in this direction, we see lots of gamma ray emission, lots of X-ray emission, lots of activity from the central black hole engine. And so those galaxies are called blazars. But if we look at the same system, but the galaxy is tilted or oriented in a different direction, we actually observe different types of phenomena, and so we actually have different types of galaxies, even though the central engine that's driving this emission might be the same. And so we think that this took a long time for astronomers to figure out, was that there were all sorts of different types of galaxies with very active black holes, but they were probably all due to the same phenomena. So going back to this animation here, what we're basically seeing is that about 90% of these sources are those blazars that I just mentioned. So these are galaxies where we're looking straight down the barrel of that black hole engine. And if we zoom in to one of these sources, this is a source with a horribly non-instructive name of FSRQ4C plus 2807. So that's this galaxy, and this is a model of what that part of the sky looks like. And you can see that in addition to this very bright source, there's actually about 15 other relatively bright sources that were also detected by the Fermi satellite. And what they basically did was you can take, so the astronomers who were part of this team basically catalog these 1,500 sources and into a big searchable database online. And so any astronomer, or really anyone, can go online and pick a particular source, and then you can actually download all the data that's associated with the source from the catalog. And so this is 11 years worth of data for this particular object. And the way it's plotted, you can see that there's time along the bottom. So 2009, remember the satellite was launched in 2008, but we have data going back to 2009. And here is 2020 towards this end of the plot. And so these are just all the measurements of how this black hole engine changed in brightness. So you can see that right now it's not very active, so it's not very bright. But in the past, it has had these spikes of activity where the gamma rays have spiked, and that presumably is because material was falling in towards the black hole, again getting jammed up in the accretion disk and heating up to tens of millions of degrees, and hence you're getting these spikes in activity. And basically this repository of all this data, these so-called light curves, again, the light curve is basically just a plot over time of how the brightness in gamma rays changes. This is a catalog that astronomers can search through, and they can basically use this to help them do their research. So if they have observations in other wavelengths, in the radio and X-rays, they can go and find a source in this gamma ray repository, and then find out the data for that source in this part of the electromagnetic spectrum. All right, so with that, we have a bunch of stories to go through, so I'm going to plow on through to the next story. And what we're going to do now is we're going to, instead of just looking at the entire sky, we're going to look at galaxies that are, or star clusters that are much closer to home. So this is the globular cluster M92, and M92 is a globular cluster that actually orbits our own Milky Way. So globular clusters, by their name, you get the sense that they're these tightly packed groupings of stars. So this is a relatively old image. Here's a slightly newer one, both taken from ground-based telescopes. And you can see just how many stars are in the center. And all these stars are orbiting each other. So they're basically orbiting in the globular cluster due to their mutual gravity. And this particular globular has about 300,000 stars packed within about 100 light years. So if you were to, if we were to transport ourselves into the center of this globular, we would have 1,000 times more stars in our nighttime sky, and they would appear far, far brighter just because there's just so many more stars so closely packed together. Now, one of the reasons why astronomers want to study systems like this is because we think that these stellar clusters basically all formed roughly at the same time, and all these stars are packed together, very tightly, so that they're roughly at the same distance. And so you can basically study how populations of stars form and how they evolve over time. If you just look at stars that are spread out through the galaxy, you don't necessarily know that they formed at the same time or they're at the same distance. Some stars could be brighter than others, and so that can complicate your research. But here, you have everything all packaged together, makes it really simple. So this is a really nice ground-based image of M92, and what I'm going to do now is show you the same globular from the James Webb Space Telescope. So here it is. And then I'll explain why there's a huge gap in this image in just a minute. This is using James Webb's two near-infrared imagers. So the James Webb Space Telescope, unlike the Hubble Space Telescope, which can observe in optical light, the visible light that our eyes are sensitive to, James Webb only observes in the infrared. And the reason, one of the reasons why is that you can, in the infrared, you can peer through a lot of the dust and gas that blocks or obscures starlight. And so in this case, when we look at star clusters, we can actually see more stars unobscured. And because James Webb has a larger mirror, it's much more sensitive. And so these observations, all the observations that were made for this study took hours, and the equivalent on Hubble would be hundreds of hours to reach the same levels of sensitivity. And so this is about an hour's exposure is what we're seeing. And so what is the reason for this big gap in the middle? And that has to do with the fact that, well, the gap actually exists. So if you look at the different detectors on the James Webb Space Telescope, here's the near-infrared camera. There's also a mid-infrared camera, and then there are two spectrographs as well. And so there are, just by the nature of how these detectors are set up, there's a natural gap. But the reason why they decided to put the gap right in the center of the globular cluster is because they really wanted to look at the very faintest stars. And so what that means is that they wanted to have a long exposure, up to about an hour. And if they did, if they put the center of the globular at the center of this frame here or on this side, what would happen is that all the stars in the center would completely saturate, and you wouldn't actually get any information at all. So they made this decision to put the center of the globular cluster in that gap so that they would have really good data on the faintest stars in this image. So here is just a zoom in just to how many stars are in this region. And this gives you a sense of what the scale is. So this bar is 2 light years. So the group of astronomers who did this work published a paper this month. And the paper lead author was Daniel Weiss, who's at the University of California, Berkeley. And there's 41 other authors, so there are 42 people involved in this project. And this gives you a sense of just how big a lot of astronomical research projects are now, where you often have dozens, if not sometimes 100 or more astronomers involved in these studies. But actually, one other thing is that this was something called part of what was called the Early Release Science Program. And in 2017, so before James Webb was launched, JWST was launched on Christmas 2021, but NASA sent out a request for proposals, and the idea was that astronomers could propose a science program for JWST, and these observations would be done first, but part of allowing the astronomers to basically get ahead of everyone else and get their observations done first is that they would create and test software to analyze and reduce the data from JWST. And then once they create the software, they would then release it to the rest of the astronomical community. So basically, this is using the services of astronomers to help create software that would benefit the entire community of astronomers that are using this telescope. And the tools and the data that come from these observations would be made public, so any astronomer, even those who are not part of this team, would be able to access this data immediately. So it turns out that for this paper, they didn't just look at M92, but they also looked at 2 additional clusters of stars. So one of them is Draco 2, which is a small satellite galaxy to the Milky Way. So it turns out that, you can almost think of the globular clusters as small satellite galaxies because there's about 150 globular clusters. They all orbit around their Milky Way. There are almost 60 small satellite galaxies, the largest of which are the Magellanic Clouds, which you might have heard of, and they also orbit around our Milky Way. And except in this case, this globular is about 26,000 light years away. This satellite galaxy, the smaller galaxy, is about 65,000 light years away. And in here, their third target was a small dwarf galaxy that's about 3 million light years away. And so they wanted JWST to explore the stars in all 3 of these clusters of stars. And this is a somewhat confusing plot, but basically what you can learn, and I'm not going to really explain what the numbers and the symbols quite mean, but we're basically taking the observations from all the stars that have been measured from James Webb, And we're plotting, and you can take those numbers and basically get a brightness of the star along this y-axis, so along this direction. So the brighter the star, the higher up you put it in this plot, and the dimmer the star, the further down towards the bottom that you put on the plot. And then the other bit of information that you can get from the light information from JWST is how hot and how cool the stars are. So hotter stars are further to the left in the plot, and the cooler stars are further to the right in the plot. And so basically what they're able to do is by plotting the stars or the information that's gathered about these stars in this way, they can actually figure out that JWST is actually observing the dimmest stars that are possible. So it turns out the stars down at the bottom of this plot are right at the edge at which nuclear fusion is possible. So for stars that are about 0.08 solar masses, so 8% the mass of our sun, that's actually the smallest star that you can have and have hydrogen fusion occurring at its core. So this is the most accurate or most sensitive detection that we've made of stars, the faintest stars at the bottom, but James Webb was able to find the faintest stars in the M92 globular cluster. For Draco 2, they did something similar, where again they found the faintest possible stars. In this case, the lowest limit is about 0.09 instead of 0.08, so just above that minimum hydrogen burning limit. And then for this galaxy, this dwarf galaxy, they were able to find lots of stars, but they were also able to find stars that are in this part of this particular part of the diagram, and these are stars that are at the end stages of their lives. So you might have heard of stars like that are called red giant stars, and once this is something that our sun will turn into 4 or 5 billion years from now, where it balloons up into a big red giant star. Hence its name. And it turns out that those stars end up in a completely different part of the diagram compared to stars that are in their normal parts of their ordinary lives. So, what this research is showing is that JWST is a great telescope and tool for helping us understand these stellar populations. All right, so we're going to switch to our next story. And this is, we're not quite into the solar system story just yet, but this is just an image of all the planets in our solar system. And these are to scale. So that, this is how big the sun would be, and then this is how big all the planets would be if you were to bring them all really close together. So here's Earth, which is roughly about the same size as Venus, and each of these is about twice as big as Mars. But then as you move away from the inner solar system to the outer solar system, you suddenly jump in size to these gas giant planets. We have Jupiter, Saturn, and then we have slightly smaller Uranus and Neptune. And so in the past 25 years, 28 years now, astronomers have discovered more than 5,000 planets outside of our solar system. And one of the big questions that astronomers and lots of people have long wondered is whether our solar system is what is common, this type of architecture of our solar system. We have inner planets that are small and outer planets that are large. Is this common in the universe, or at least in our galaxy? Or is this something rare? And how common are Earth-like planets, and so forth? And so in a paper that was published just this past month, again, by 4 astronomers from Switzerland, from the University of Geneva and the University of Bern, they basically started looking at all of the planetary systems that have been observed, as well as solar systems that have been modeled. So astronomers have built a lot of computer models to describe how solar systems can form. And what they discovered is that there's actually 4 different types of solar systems out there. And so the first one is the so-called ordered type of solar system. And this is the one where that's similar to our own solar system, where you have planets that sort of increase in size as you go further out. So the inner planets are the smallest, both in size as well as in mass. And as you go further out, you get much larger planets. And they also discovered that you can also have another category of solar systems that they call anti-ordered, and that's just the reverse of the ordered one. So here you have planets that are big on the inside and small on the outside. And there are 2 other types of architecture. One is the mixed system, where the sizes of the planets are kind of jumbled. So it doesn't really matter where they are, distance-wise from their parent star. You can have a mix of small and large planets. And then you also have systems that are similar, meaning all the planets are very similar. Actually, there's even a term for this. They're called peas in a pod, because peas are all the same size. And so this is so basically this team came up with this framework to describe the huge number of solar systems that have been observed. And here is how they break down the solar systems that were created through computer models. So these are synthetic solar systems. These are not real solar systems. And this is kind of confusing, but these each vertical line represents one solar system. And so you can see that they've organized these solar systems into anti-ordered, similar ones where all the objects are similar sizes, ordered ones where you have smaller objects closer to the sun, larger objects on the outside. This is the reverse. So these objects down here are further from the parent star. And then you have the mixed systems where you have the planets all jumbled up. And then it turns out that when they look at these computer-generated systems, 80% of their systems fall into the similar category, meaning all the planets are pretty much the same size. And 8% each fall into the mixed and the anti-ordered. And only 1.5% are in the ordered category. So remember, the ordered category is the category that our solar system falls into. Now, this is looking at these computer-generated models. What happens if you try to compare this to actual observed solar systems? So unfortunately, out of those 5,000 planetary systems or planets that have been discovered, many are only one or in single planet or double planet systems. And that's not because those star systems don't have a lot more planets. It's just that we haven't found more planets yet. But let's take a look at the observed solar systems, and what they find is that 59%, so almost 60% of the observed solar systems are under this similar category, where all the planets are very similar to each other. Just over a third are ordered. So again, the smallest planet are on the inside, the largest planets are on the outside. Just 5% is mixed. And then surprisingly, there are no planetary systems that we've observed that are anti-ordered, where you have bigger planets on the inside and larger planets on the outside. And this, seems to be very puzzling in the sense that, why would you have such a very different mix? And it could be that the computer models are not quite correct, but more likely what is happening is that our observations are incomplete. So it turns out that the way that we find planets, it is really easy to find planets close in that are big. But if you want to find planets that are small and further out, it's actually much, much harder. So it almost makes sense that you won't find these anti-ordered systems. So right now, this is just some preliminary work that helps frame the question of how solar systems are organized. but this is a kind of a great first step to helping both observers and people who run computer models sort of think about how to organize their own thinking about what the solar system, the architecture of these solar systems are. All right, so I'm going to keep kind of getting closer to our own solar system and home, and also coming down in size. So instead of just talking about entire solar systems, I'm going to talk about the so-called eyeball planets. And eyeball planets are basically planets that have one part of the planet facing their parent star at all times. And so what happens is that one side of the planet gets baked, and in the other side, since it always faces out towards space, away from the star, this side of the planet gets frozen. And the reason why they're called eyeballs is because you have something that sort of looks like an eye, depending on if you're looking at it from the right direction. And so if you have a frozen side on one side and you have a desert side on the other, you can imagine that the region in between these two could be actually pretty nice. Instead of being frozen or being a desert, you might actually find water or a region that's habitable to potential life. And the reason why we think these eyeball planets might exist has to do with the different types of stars that we find that support planets. So our sun is what's known as a G-type star. And if you look at the amount of radiation and heat that's coming out from the sun, you can actually define a zone, which is colored green here, that we can call the habitable zone. So planets that are in this habitable zone can have liquid water on the surfaces of rocky planets. And so inside of this green band, in this habitable zone, it's too hot for liquid water to exist. And then on the outside, it's too cold, and so you can sort of get a sense that that's supposed to be a snowflake. Now, there are stars that are brighter, more massive, more luminous. They put out more energy than our sun. So in this case, the A star also has a habitable zone, but the habitable zone is further out. And that's just because the star is more energetic. And so you have to move that zone out. And then on the other end of the scale, we have these M dwarfs, these M stars that are dimmer than the sun. They're redder. And as a result, this planet has to be much closer in for it to be in the habitable zone. And when you have planets orbiting close in to the M dwarf star, it's actually very easy for these planets to get tidally locked. And by that, I mean where one part of the planet always faces the central star, and then the other side of the planet always faces away from the star. And so this is just something that happens. And as a result, you can imagine that these eyeball planets could very well exist because it's so common, it's so easy for these planets to be tidally locked. And in fact, there's one planet that we know of that is probably like an eyeball planet, and that's the planet that's been discovered around Proxima Centauri, which is the closest star to us. So just over 4.5 light years, or 4 1/3 light years away. And this Proxima Centauri b was found, I think, in 2015, and people immediately started writing papers about it. And so one of the theoretical models about what this planet might look like, this is a model of the temperature. So this side is the side that always faces the sun, Proxima Centauri, and then the other side always faces space. And so if this particular planet, which is about 1.25 times Earth's mass, if it has a thick atmosphere, the researchers on this paper, they realized that you can actually have liquid bodies of water on the nighttime side based on how close it's orbiting to the star. And depending on how thin or thick the atmosphere is, those bodies of water could be frozen or they could be liquid. And there's even the potential, depending on the sort of the parameters that you throw into the model, for a global ocean to exist. So we know, these planets are likely. We even have examples of planets that we've observed that are probably eyeball planets. And so we come to this recent paper by Anna Lobel at the University of California, Irvine, along with her collaborators. And what they did was to model eyeball planets using global climate circulation models. So the same sort of models that we use to model climate here on Earth, they apply it to these eyeball planets, and this is what they find. So again, what we're doing is we're taking the entire map of the planet and we're flattening it out onto this 2D map. So as you can imagine, this is the part of the planet that always sits underneath the star, and the other opposite side is kind of spread out along the edges here. And so this is a temperature map showing what the difference in temperature is. And these arrows show the wind directions. So this is something that actually happens on Earth as well. If you have a lot of heating on the ground, the hot air rises. And so as the hot air rises, cooler air from beyond rushes in to sort of fill in the low pressure area. So that's why you have air moving towards the center of this hotspot. And then this, is the basically showing the winds on the surface of the planet. This is showing the winds higher up in the atmosphere. And so what this is showing is that as the air rises, it will tend to cool off, and then the air will then tend to move off away from that hotspot. And again, this is something that's observed here on Earth. And the color basically represents the height of the atmosphere. So for rising air, the height of the atmosphere is higher than elsewhere on the planet where the air is descending or cooler. And then the other thing that they were able to show is just the amount of clouds that you would expect on this planet if there was a lot of water on the planet. And so the color represents how bright the planet looks at the top of the atmosphere. So basically, if you have a lot of evaporation, you expect a lot of clouds, and you expect this part of the planet to be brighter than the other half of the planet where there aren't any clouds because there's not enough water vapor in the atmosphere. And then this figure here shows how much rain or how much precipitation is occurring. So much of the evaporation is occurring right at the center, where just below where the star is shining, and as the water vapor moves up and moves off away from the center, it cools, and then you basically have rain. And so basically, what they were able to show is that it is indeed possible to have sort of temperate climate zones along the edges of this eyeball, or the center of the eyeball. And depending on the type of planet that they're looking at, whether it's a water world, it turns out that if a planet is mostly ocean, then there's going to be so much evaporation, you're going to get this thick, cloudy atmosphere that completely blankets the planet. But if you have a lot of land and not that much in the way of oceans, you can have what is pictured here, where you have liquid bodies of water along the so-called terminator, the dividing line between the sunlit side and the nighttime dark side. And then on the other side, you basically have a frozen wasteland where the water is precipitated out into ice that covers the backside. So this is kind of a wonderful theoretical work or computer modeling work, but it helps astronomers think about how to observe these planets when we build telescopes that are able to observe these worlds in detail. So JWST probably won't be able to really observe or confirm the existence of such a world, but future telescopes might be able to do that, and by knowing how these planets are organized, that will really help us set up those observations in the future. All right, my last story and we'll finish up in just the next couple of minutes, is about the double asteroid redirection test, which is the DART mission. And this was the mission that smashed into an asteroid back in September of last year. And the reason why planetary scientists wanted to do this and why this was supported by NASA is because there are thousands of asteroids that are in orbits that cross the Earth's orbit. And so these are potentially hazardous, and we want to keep tabs on them so that we want to know whether one might be on a collision course with us here on Earth. And if one does turn out to be aimed at the Earth in the future, we want to be able to have tools that can allow us to divert these asteroids so that they don't hit the Earth. And so the DART mission is the very first test of trying to change the orbit of an asteroid by colliding it with a spacecraft. And so it was this mission was sent to a double asteroid. So the larger asteroid is Didymos, and the smaller asteroid is Dimorphos. And the DART spacecraft was launched to impact the smaller Dimorphos asteroid. And here is how it's supposed to orbit. And so the idea is that if you hit it, you should slow it down so that you can cause the orbit to change. And the goal of the mission was to see how much of velocity change you can have with this collision. And so when this collision happened last September, there were a number of pictures that were beamed back as the DART spacecraft headed towards its sort of collision point. And so here is Dimorphos off in the distance. And Dimorphos is about 170 feet across, so just slightly larger than 1.5 football fields. So it's not very big. And we're going to just see, you can see that it doesn't look like a solid piece of rock. In fact, it looks like there are a bunch of boulders on the surface. And when we zoom in, you do indeed see, get a sense of a lot of boulders, a lot of stuff that looks like gravel on the surface. And then here's the image right before, this is the last image that was sent back right before impact. So basically, was cut off. But the planetary scientists were able to take the data that they had gotten back, and they were able to get to recreate some of the highest resolution images of the surface. So this bar is 3 meters, so about 10 feet. And so again, you get the sense of these gigantic boulders that litter the surface of Dimorphos. And here we're going to zoom in again. And basically the impact was right at the center between these two boulders. And the spacecraft was aligned in such a way, you might remember the spacecraft has these 2 solar panels. Basically, each solar panel smacked into the boulders on either side, was how the spacecraft was aligned. And just a few weeks ago, NASA released these Hubble images taken in the 2.5 weeks after the impact. And so I'm going to play this animation over again. So Didymos and Dimorphos are so close together that you can't actually distinguish them. So both of them are inside that dot in the center. So let's replay this. And so we start out just a few hours after the impact, and then we're basically watching it. Here's 2 days, 3.7 days, 4.7 days, 5.7 days, 8.8 days, 11 days, about 15 days, and then finally 18 days. So basically there was a lot of stuff that got ejected out. And what Hubble was able to find is that the initial impact created what they call the ejecta cone. So basically material got sprayed out in this direction. You can see a set of dotted lines, or a dotted line that shows you the direction of this material that was shot out from the impact. So dart came in from this direction, hit it, and the material spewed out towards the upper left. And just a day and a half later, 1.7 days later, they were starting to see the ejecta curving. And it's kind of hard to see, but you kind of get the sense that there's a slight curve to these trajectories. And what is happening is that this material, the dust, the rubble that's been ejected, is starting to be affected by the gravity of the main asteroid. So that's why it's curving. And then over time, over the course of the next several weeks, the finer material is now getting stretched out away from the system. And what's happening is that the solar wind and the pressure from light from the sun is actually pushing away the smallest particles. And so that's what we're seeing here. And we're starting to see this tail. So just the same way that comets can have tails as due to pressure from the solar wind, you're seeing the same sort of thing with this asteroid. And so what the end effect of this impact was that it actually did change the orbit of Dimorphos. So previously, before the impact, its orbit was 11 hours and 55 minutes, so just 5 minutes shy of 12 hours. And after impact, its orbit was reduced, the orbital period was reduced by 33 minutes, which meant that there was an enormous change in the orbit. And so this was a validation of this particular technique of how you can redirect an asteroid. And now I think one of the most interesting things that come out of this is that based on observations of Dimorphos, but also observations of other asteroids that we've visited. So both the US and the Japanese have sent spacecraft to other asteroids. They've gone to actually pick up material from these asteroids to return them to be studied on Earth. But in every single one of these cases, these asteroids seem to be more like rubble piles than they are, like giant solid chunks of rock. And so there is now a suspicion now amongst planetary scientists that perhaps most asteroids are actually like rubble piles. And so this is very important to know because what sort of interventions you use to redirect an asteroid, you might have to think about carefully depending on what the structure of the asteroid is. So something that's completely solid will behave differently than something that's just a loosely bound pile of boulders and gravel. And so it's really important for us to study these asteroids up close to really determine their nature so that we can, if something does threaten us in the future, we can find a technique that is the most appropriate for sending it on its way, to redirect it and get it, keep it from hitting the Earth. Right, so with that, that's the end of my stories. And I know it's getting late since we had a late start and we had all sorts of technical issues. But I'm happy to take questions from the audience. But if you have to leave, it is a school night. Feel free to take off. But thanks, everyone. And actually, before you go, I just wanted to show this last slide that our next 60 Minutes is on April 26th. And it'll again be here in Ricketson Auditorium. So thanks a lot. Yes? Okay, is it possible for our planet to become an eyeball planet? No, just because in order for a planet to become an eyeball planet, it has to, I said earlier that eyeball planets orbit really close to their star, so you'd have to move the Earth closer than Mercury is orbiting our sun. So there's really no way for us to move the Earth in that way. So it's very unlikely for the Earth to become an eyeball planet, unless you have some kind of magical way to do it. Okay, a second question. If the Earth would stop orbiting around the sun? Oh, if the sun would stop spinning, Well, again, that's sort of a magical theoretical question, because there's nothing to stop the sun from spinning. But it wouldn't affect the orbits of planets that are orbiting around the sun, because that our orbits only have to do with the amount of matter in the sun, how massive the sun is. But if you stop the sun from spinning, it probably would affect how magnetic fields are generated in the sun, and it would probably affect the generation of solar winds and coronal outbursts. So there would be effects, but it wouldn't affect how planets orbit around the sun. Okay. Yes, sir.
The Marcos slowed down more than was predicted. Do we know, have a good idea yet whether it's because we hit the center of mass really well, or threw off less ejecta?
Yeah, so that's a really good question. DenverMuseum seem to have changed the orbit, or its orbit was changed much more so than people had initially thought. And part of the issue is the fact that there was this enormous ejecta that got sprayed outwards, and it got sprayed outwards in the opposite direction. And so if you think about the momentum that was transferred, if let's see, you have Dimorphos coming in this direction, and you have DART coming from this direction. So if all of the momentum of DART landed on Dimorphos, but nothing got sprayed out, then we can actually calculate how much the momentum change would be. But what happened was that in addition to the momentum in this direction, you also got an enormous amount of material that sprayed out in this direction. And so that basically means that from Newton's third law, you have this reflex motion of you actually had more momentum pushing it against it in this direction to account for the material that's coming out in this direction. And so that was basically this factor that allowed Dimorphos to have a bigger change. And so during that collision, there was basically given the energy that was released and given the dynamics of that rubble, you can imagine that some scenario where everything was absorbed and nothing got sprayed out, in which case you wouldn't have as much of a momentum change. But in this case, because of this spray, that added to the momentum change. And so it probably does have to do with not only the amount of energy, but the material, how it was what that aggregate was and how it reacted to this impact. Yes. What would happen if a ray of the sun, the sun rays meaning from Dimorphos, or would, okay, if our sun had, solar flares, okay. Okay, thanks for that clarification. So as I mentioned earlier, the sun does have these explosive phenomena, these coronal mass ejections, solar flares, and these result in not only bright X-ray emission, some gamma ray emission, but it can also result in these big bursts of charged particles. So the light from the sun, the X-rays, the gamma rays, they travel at the speed of light. So we can see them in 8.5 minutes. So if something happens on the sun, we'll see it happening 8.5 minutes later. But the charged particles, they can travel many thousands of miles per second, if not tens of thousands of miles per second. And those particles can take multiple days to get to the Earth. And it does turn out that these particles can have an impact on the Earth, and that's just because so much of our modern society relies on electrical power, relies on electric transmission lines, moving that power around, relies on just a lot of equipment that can actually be affected if you have these large pulses of charged particles hitting the Earth. And so in, I think, 2013, I might be getting the dates wrong, but there was actually a solar flare that took down actually it might be 2003, that it took down the power grid in Quebec and northeast North America. And that was the result of flares affecting power equipment and basically sort of a cascade effect because the power companies weren't expecting this. So astronomers, people who study the sun, who actually do worry about this, and they constantly advocate that the government spend more money to study the sun, but also to be prepared so that if part of our power infrastructure gets knocked out, we have the resources to basically fix things. As it is, from what I remember, we are actually woefully unprepared right now. So that's not a totally happy story, but something to think about. And you said you had a second question? Oh, what do I do as an astronomer? So I work here at the Denver Museum, and half my time is spent actually giving talks to the public, like you, here tonight. And I also do research in astrophysics. My background is in star formation, so I do research in studying how young stars form. I'm currently looking at clusters of young stars. And I also look at how we can teach astronomy more effectively as well. Thank you. Any other questions? Yes?
What do you think the biggest threat is to Earth, whether it's black holes or environmental or asteroids or ozone layer?
Well, yeah, what are the biggest threats? I mean, the question is, are you talking about a threat to the entire planet, or a threat to biosphere, or a threat to the human species? Asteroids are threats that we know can almost completely destroy all life on the Earth. I mean, we've had cases where, everybody has probably heard about the asteroid that killed off the dinosaurs, and so those are threats that can not only destroy all human civilization, they could potentially destroy a significant fraction of our biosphere. So astronomers and planetary scientists are clearly worried about those threats. Things like black holes and are not so much of a threat because oftentimes people think of black holes as being like these vacuum cleaners in space, but for the most part, things can orbit around black holes perfectly fine without getting pulled in. You have to be on a very specific trajectory, or you have to lose energy in your orbit to fall into a black hole. So one thing that you can take away is that if our sun was to, we talked about these magical scenarios. If our sun was to magically turn into a black hole, all the planets would continue to orbit around it, because the only thing that it would change, it wouldn't really change anything except for the fact that we would no longer get light or heat from the sun, but and so we would all freeze. But presumably the mass of the black hole is the same as the mass of our sun, so that the orbits of the planets wouldn't change. People do wonder about supernovae that can go off, and so there are ideas, speculations that in the past a nearby supernova might have wiped out the ozone layer, or otherwise had harmful radiation disrupted life on Earth. But currently there's no star that we know of that's close enough to do that. Let's see. We mentioned solar flares. So those type of things could potentially cause incredible disruption to modern civilization, just because like I said earlier, we don't have like a backlog of equipment that we can go and swap in if all of our power infrastructure fails because of a solar flare. So you can imagine the sort of disruptions that can occur. Things like, I think I would worry about. Part of the problem, and I don't want to say, part of the problem is understanding. Not only the risk of, how damaging a hazard is, but what the probability is. And so I can't give you off the top of my head, how I would balance, the risk versus, the probability. But I think, the top three would be some ejection from the sun, asteroid impact, and also climate change as far as, impacts on human civilization. Yes.
As far as climate change, for example, when we talk about rain, precipitation, and that was just a theorizing what it would be like if there was a planet with water. Do they actually know of any planet with water that has precipitation?
Okay, so the question is, have we actually observed planets with huge amounts of water and presumably a lot of rain? And right now, none of our observations have the sensitivity or have the resolution to really let us figure out what the surface of the planet is made up of. We're able to get a very crude understanding of the atmospheres of a very small fraction of the planets. JWST is actually helping us a lot in determining, making some preliminary guesses as to the atmosphere, what the atmospheric composition is for some of these exoplanets. But it turns out that, it's still very rough in the sense that you can have multiple interpretations given the data that we have. So we'll need better telescopes. Now, astronomers do think that water planets could very well exist because what they've done is they've run a lot of computer models of how planetary systems form, and based on what we know to be the makeup of the nebulae that planets and stars form from. So we know that water is actually a very common molecule in the universe. So it's actually very likely, given these scenarios, what the makeup of molecular clouds are, and our understanding of the physics of star formation and planet formation, it is very likely for planets to have, you can have dry worlds, you can have wet worlds, you can have extremely wet worlds where oceans not only cover the entire planet, but you might have, 50 times or 100 times the amount of water that exists on the Earth you would find in one of these water worlds. So water worlds are still speculative, but they are based on our best understanding of current science. Yes, one last one.
Yeah. Are astrobiologists aware of the biology of bioprecipitation? In other words, for example, here in Colorado, there's a headquarters for SNOMAX that makes artificial snow. And in order to do it, there's a biology. They have to culture a microbe called Pseudomonas syringae, and then an ice nucleating protein forms that it doesn't have the water vapor doesn't have to be as cold as if you seeded a cloud with silver iodide or in other words, in nature, there's a biology to our rain water cycle. Do astrobiologists recognize this? Are they communicating with the terraforming possibilities not only here on Earth but anywhere else for water?
Okay, so the question is, it appears that biology is an important factor in whether rain clouds form, and are astrobiologists paying attention to this type of research? And I guess my answer would be, you have to go ask an astrobiologist, because unfortunately, I can talk about some of the broader ideas in astrobiology, but I don't know enough about some of that research to answer your question. Okay, maybe one last question. Okay. All right. So, how much energy did the Dimorphos impact? What was the total energy involved? And I think, did you ask that in an earlier presentation? Okay. No, unfortunately, I never made that calculation. So you would have to calculate, what the impact speed was with the mass of the spacecraft. And whether we're going to go back to the planetarium, I guess right now the answer is no, just because this space seats more people than the planetarium, and the only advantage in the planetarium would be if we utilize some of the planetarium software to show visualizations of some of the phenomena that I would be talking about. But currently, because I'm the only person during these presentations, it's just as it takes me just enough effort to get one of these out on time on the day that it's supposed to come out, and so I don't have the bandwidth to do stuff for the planetarium, unfortunately. All right, so with that, I want to thank everyone for coming, and we'll see you next month.